Hello.
Sir, please unmute yourself. Sir, you are not audible. Please unmute your. No, sir, you are not audible.
Hello.
Yes, sir, you are audible.
Thanks. Hello.
Yes, sir.
Hello. Hello, everybody. We will start our lecture series. And in this lecture series, Saprativ is going to talk about the decarbonization in alumina plant. And his exact topic is, as you know, his exact topic is just 1 minute. Yeah. 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 This is about mechanical vapor recompression, a technology for low carbon alumina refining. So he's MTech and highly qualified and working in R&D in Vedanta, and he's quite active in this field. And now I request Saprativ and our office to run his video, and after that there will be a question answer session. Over to Priyanka.
Yes, sir.
Hello, I am Saprativ Basu, working as lead scientist in R&D Vedanta Aluminium in Odisha, India. I am a chemical engineer by profession and have 10 years of research experience in modeling and simulation in industrial R&Ds. Today, I welcome you all for an exciting session on the topic that is mechanical vapor recompression and how it can be used in alumina refining to reduce carbon footprint. These are the list of topics that I will try to cover today. At first, I will explain the need of decarbonization in aluminium, especially alumina manufacturing. Then we'll see the emission level comparisons for different steps of the primary aluminium manufacturing. The target of the reduced CO2 emissions set by International Aluminium Institute under net zero emission scenario will be discussed. What are the possible pathways to decarbonize the aluminium industry? What is the alumina manufacturing process? The mechanical vapor recompression, what it is, where we can use this technology to reduce carbon footprint, that will be discussed. How we can use this technology for existing plants as retrofit options. We will discuss a case study of one of world's leading alumina refinery, how they are evaluating MVR as an alternative to decarbonize refining. After that, for different steps or unit operations of refining, how we can retrofit
There is no voice.
Sir, let me check.
for an exciting session on the topic that is mechanical vapor recompression. Then we'll see the emission level comparisons for different steps of the primary aluminium manufacturing, the target of the reduced CO2 emissions set by International Aluminium Institute under net zero emission scenario will be discussed. What are the possible pathways to decarbonize the aluminium industry? What is the alumina manufacturing process? The mechanical vapor recompression, what it is, where we can use this technology to reduce carbon footprint, that will be discussed. How we can use this technology for existing plants as retrofit options. We will discuss a case study of one of world's leading alumina refinery, how they are evaluating MVR as an alternative to decarbonize refining. After that, for different steps or unit operations of refining, how we can retrofit MVR and what are the advantages. Different types of compressors and carbon abatement scenarios will be discussed. Last, I will summarize my talk by mentioning the advantages and challenges of using this technology. Aluminium is the metal of future because of its inherent properties. It is lightweight yet strong, easily recyclable, highly temperable, and which is why it is the second most important metal in the world today. The primary aluminium manufacturing process starts from mining of bauxite ore, the extraction of alumina, which is the oxide form of aluminium though, under high temperature and pressure, production of metallurgical grade alumina, and finally the electrolytic smelting of the hot molten aluminium metal. Sub-secondary aluminium manufacturers also use scraps for hot metal production as well. We'll focus today on the alumina refining. If we consider the primary aluminium manufacturing, about 15% of the total greenhouse gas is emitted from alumina refining. Though it is lesser than that of the electrolytic smelting process, contribution towards emission is on the higher side. To be specific, around 70% of the greenhouse gas emission comes from the digestion circuit of the IBAAS process of alumina refining, and approximately 30% during the high temperature calcination process, which is basically to remove the chemically bonded water molecule from the aluminium trihydrate, which is ATH. Under the net zero emission scenario, or the NZE, these are the targets that are being provided by the International Energy Association. The emission intensity and the total emission for primary aluminium making need to be brought down significantly by 2030 if we want to restrict the global warming within 1.5 degrees C by 2050. If the global fuel consumption is analyzed, China consumes mostly fossil fuel. Europe, North America has already started its transition towards renewable energy resources. It is mainly due to the abundance of those fuels in those region. Asia Pacific region also is a heavy consumer of fossil fuels, but nowadays, as per statistics, some percentage of the demand in Asia Pacific is being met by the renewable energy resources as well. As per International Energy Association statistics, around 3% of direct CO2 emissions comes from aluminium industry. This plot shows a comparison of the current emission level, which is around 16.1 ton of CO2 per ton of primary aluminium. If business goes as usual, which is the 2050 BAU scenario, by 2050 the emission levels will be somewhat similar and the global warming will rise, will not be able to control. But if we want to restrict the global warming by 2.5 degree, then the CO2 emission need to be cut down heavily, significantly. The emission from electricity production, which is shown here by the green bar, need to be completely clean, free of CO2. Whereas the direct process emission also need to be reduced by half, which is basically the yellow portion of this bar. If extrapolated for different scenarios, the CO2 emissions are predicted and reported by International Energy Association as well. Up to now, we have discussed the current emission levels and the need to decarbonize. Now, let us shift our focus on the alumina refining by IBAAS process. Bauxite ore are processed as 140 to 170 degrees centigrade to extract alumina, which is referred to as the low temperature digestion process, and around 250 degrees C or more than that for high temperature digestion to achieve good alumina recovery depending on the bauxite ore type. In both cases, the bare liquor, which is a recirculating solution of caustic soda, dissolved aluminium, and water, is heated to the required temperature using steam. The hot bare liquor extracts the alumina bearing components from the bauxite, which is known as the digestion process. The residual solids are removed by washing, and the liquor is then cooled to precipitate alumina trihydrate crystals, which is known as the precipitation part. Then it is collected, these crystals are collected and calcined to form alumina. The remaining spent liquor then reheated to extract to evaporate the water part, the moisture part, and some water is removed by evaporation to increase the caustic concentration, which is used again for the as a cost recovery or the recirculation back in the digestion process. Traditionally, steam is supplied to the digestion process from coal-fired boilers or as discharge from the steam turbine of a combined cycle electric power plant. In case of low pressure refinery, the high pressure steam is used for electricity generation, and medium to low pressure steam is used for the process heating as a refinery energy input. It has been seen significant amount of the energy input of the refinery leaves as a low grade heat and unable to be reused with the current technology or the existing technology. Renewable energy driven mechanical vapor recompression, which in short we know as the MVR, provides the opportunity to replace the need of fresh steam generation by reusing the waste vapor which is currently emitted in the atmosphere, and therefore reduce the need of the fresh steam generation within the bare process. And finally, in turn, it reduces the fossil fuel consumption. The MVR powered by renewable energy represents an attractive and sustainable means of upgrading and reusing the low temperature waste vapor from the digestion step, and also it can be recovered from other steps as well, like calcination, evaporation, like that. In the next slide, we'll discuss about the process of MVR. Mechanical vapor recompression or MVR is a technology based on the reuse of waste vapor as a heating medium after having increased its temperature and pressure by mechanical compression. A typical MVR equipment is a set of compressors or which can be centrifugal or axial, which increases the temperature and pressure of the vapor. In the figure, an MVR setup for falling film evaporation is shown. From the top, the spent liquor comes and flows through tubes which are inserted in a shell. The shell uses fresh steam for the initial energy required to evaporate the solvent inside the spent liquor flowing through the tubes. The mix of evaporated vapor and the concentrated liquor, when comes to the bottom of the chamber, the vapor is separated. This vapor is currently sent to the cooling towers for heat recovery. But after the implementation of MVR, the vapor is sent to the vapor recompressors. The set of recompressor, it can be one or two or many, depending on the requirement, the temperature and the pressure of the vapor, which are currently, these compressors are currently electrically powered, and these increases the temperature and pressure of the vapor. Once the energy content matches to that of the fresh steam, which is initially used, it can be used as a replacement of the fresh steam, and it can be reused in the shell. This way, we can reduce the fresh steam requirement, which in turn reduces the fossil fuel consumption. Here we should keep in mind that the electricity that is provided to fuel or energize these compressors need to be sustainable or renewable source energy. Then only the benefit of reducing the steam requirement can be leveraged. From the Carnot cycle on the left hand side, it can be seen that the enthalpy, the entropy diagram of the MVR, the energy required for the evaporation of the solvent, which is basically the enthalpy difference from point A and B, is roughly corresponding to the heat released during the condensation from point E to from the vapor to the liquid stage, that is the point E to F. Now this difference in the energy is basically provided by raising the temperature and pressure of the vapor, which is done in this small part of the cycle, which is done by basically the mechanical vapor recompressors. So it acts as a driving force for the energy input. In the next slides, I will present a case study done by Alcoa for their Wagerup refinery in Australia in 2021, and they have checked the installation feasibility and the commercial feasibility as well for using MVR as an option to reduce the carbon footprint in the refinery. So this I will discuss for the evaporation circuit at first, and then we'll go to other circuits as well: precipitation, calcination, digestion. But the overall concept remains the same. So at first I will discuss for the evaporation circuit. So here a typical multi-stage flash evaporation train is shown in the top figure. In conventional method, the cold liquid, which is having around 60 degree, enters a series of pressurized heat exchangers where it is heated around 140 degrees centigrade using flash vapor before further heated to around 160 using an external steam source. The hot liquor then passes through a series of flash tanks. These flash tanks depressurizes the liquor, causing it to cool and then flash off water vapor in the form of steam. The water vapor is then recirculated to the heater where it is condensed, providing heat to the cold spent liquor. The spent liquor exits the last flash tank, which is having around 80 degree. And finally, it from the final flash tank, it goes to the cooling tower where the excess energy is recovered and flexed. So now, from the cooling tower, the heat is basically recovered and sent to the power plant to the steam for the steam generation. So now it is basically a lost or waste energy. So with the MVR, the waste vapor coming from this flash tank is basically captured and it is fed into the mechanical vapor decompressors. And the waste vapor is compressed to the live steam pressure and used in the circuit. So what happens is the fresh steam requirement is lessened and consumption of fossil fuels is eventually reduced. Another key factor in this energy flow is the hot condensate from the heater 10. So if you see, this is the heater 10, the hot condensate is coming from the heater 10. So what it does is basically hot condensate presently what happens is goes to the boilers where the energy is recovered. However, with MVR, the boilers are not used. Instead, the hot condensate goes to the HTR9 just next to it, where it provides energy to the liquor which is being heated, and it continues to through the heater train to HTR1 to provide the energy to the liquor as it cools. The condensate heat recovery in this and the digestion process in the refinery reduces the overall refinery steam consumption by around approximately 5%. So this is the overall idea of the MVR, how we can retrofit in our current uh, flash tank and the heat exchanger evaporation systems. So in the next slides, other vapor sources, as I said earlier, such as calcination stack, which are having around 50% moisture content, precipitation, cooling circuits, digestion, blow up vapor, condensation, waste heat, all those are shown. So overall, the excess waste vapor available in the refinery can be collected and used with MVR. The system can be optimized to use the highest pressure available in the waste vapor to minimize the power loads. And also the series of mechanical vapor recompressors can be flexed or it can be shut down or it can be used in parallel on series depending on the refinery steam needs. So this is for the precipitation circuit, how MVR is being used that I will discuss now. So in the conventional process, energy is added to the liquor circuit in the digestion to dissolve gibbsite and energy is removed from the liquor circuit in the precipitation to extract the alumina. Now cooling water from the cooling tower is circulated to indirect liquor heat exchangers and the energy is lost to the atmosphere like the previous one also. So here basically two types of options can be done. Two types of setup can be done. One is we can flash the precipitation liquor in the flash tanks directly and then compress the vapor, and we can do the cooling water, the precipitation cooling water in the flash tanks. We can flash it and then compress the vapor. So one extra stage is required for the second one, where the cooling water is flashed in the flash tanks and the vapor is generated. From there we can be compressed. And also here in this case, as we see here, like the evaporation, the vapor from the last flash tank goes to the first stage compressor, where the need of the pressure raise, the difference between the pressure requirement is higher, and the tank just before that goes to the second MVRs. So this way we can flex or adjust depending on the steam requirement, how much MVR to use, and the steam consumption can be, optimized. So for the calcination process, what happens is basically we heat the alumina trihydrate ATH crystals to very high temperature, and it releases the chemically combined water and produces alumina. The water is lost to the atmosphere via the stack, and along with other combustion products, also it goes away. And it has been seen around 0.7 tons of water vapor per ton of alumina is lost through this process. So what they are thinking it can be done is like a proposed process is there which can capture the energy, and water vapor is to direct the stack gases to a scrubber. And in the scrubber, what happens is cooling water passes counter current to the stack gases, and heat is gained, and it condenses the water vapor from the gases. Then the warm water progresses to the 3 flash tanks in series, where the water is cooled and then recycled back into the scrubber. And the vapor from these 3 flash tanks is collected and compressed in the MVRs in a similar fashion, so that the energy inside the vapor which comes out from the calciner, it is not going into the atmosphere, but using that we can basically reuse that in the process as well. For the digestion circuit, the use of MVR is also being checked, and the feasibility is checked, and it can also be done like if we see this box, this is the existing equipment, and here also the blow of vapor which has small quantity, but here there is a challenge, because in digestion what happens, the vapor that comes off the digester flash tanks has some amount of particles inside that, so it must be cleaned before sending into the compressors, because it can erode or choke the compressors. So that's why a scrubber facility is being installed, where we can basically clean the vapor that is going to the compressors, and then we can use it in the earlier way, where it is variable speed driven systems are there, and we can depending on the steam pressure, the live steam pressure and quantity requirement, it can be recirculated in the process. So these are types of MVRs. The first one is the low speed centrifugal compressors. These compressors typically operate around 3000 or lower, and are directly driven by the electrical variable speed motors. They are robust and make up most of the MVR market, and also the technology is very proven. Then comes the high compressor efficiency and high impeller tip speed, the high speed centrifugal compressors. It has around 7000 or more than that RPM, and these are basically gear driven, and it takes a lot of space at the plant. The third one is basically the high speed axial flow compressors, which has very high volumetric capacity as well, but also very compact. So for retrofitting scenarios, it is very useful. So now we'll see the carbon abatement comparisons between the low temperature and high temperature refineries. That is the difference in the digestion pressure and temperature. So for both the low and high temperature digestion process, we need to import additional power to drive the MVR. For the low temperature refinery, additional power supply to run the MVR is needed, as well as the fresh stream replacement power generation is also need to be imported. But for high temperature digestion or high temperature refinery, only MVR power source are needed to be imported. The waste vapor compression ratio is less than that of the high temperature digestion for the low temperature refineries, and this reduces the power requirement for the low temperature refineries. And if we see the carbon displaced per ton of alumina, both are very much comparable with low temperature refineries have some amount of more carbon displacement. So now that we have seen what is MVR and how we can use MVR in the existing or the retrofitting plants, we now will say or compare that what are the existing technologies at different TRL levels and what is the usefulness of those technologies. So in coming future, electricity will become the primary energy source, and this will drive the electrification of all the industry, especially the alumina refineries, wherever applicable. Energy storage will be the key, feature or key characteristics of the alumina refineries to secure reliable energy supply. And the steam requirement via electric boilers or electrical equipments like MVR, thermal energy storage, these will go up. Then there is calcination technologies, which is also being developed, like electric calcination, various hydrogen, electric, and hybrid options, calcination technologies. These are also maturing. And lastly, the CCUS technologies, the capture and utilization and storage technologies are also evolving. And depending on the geographies across the world, these technologies will also uh, come into commercial implementation. But there are challenges to these technologies as well. Like the green hydrogen consumes very high power at almost 4 times high power than the MVR to deliver the same amount of steam to the refinery. And also the electrolyzers and storage technologies need very much high capital investment. Then there is solar thermal. We can say that this technology, while is becoming very popular, but also it cannot complete the process heat requirements. Around 40% to 50% is can be delivered. The geothermal energy is also very limited, expensive, and the technology risk is very high to completely depend on it. The energy from waste has potential, but it is very depends on the location or the existence, and it is a very unorganized sector as well. The biomass can be used as a fuel, but that technology also is not very economic, and the sector is also very unorganized. The direct electric heating is very expensive than MVR, and also it can be used when extra or excess power is available. Then only the cost will come down. The electric boilers also requires very high power in comparison to the vapor recompression technologies, and for to generate the equivalent pressure steam in the refinery, it will even need high capital investments. So now we'll see why we are backing the MVR for retrofitting as well as the new refineries in the alumina refining technology. And here I have pointed some features like the lower capital investment and operating cost than the conventional evaporation technologies, as well as zero carbon technologies when powered by renewables. In terms of technologies commercialization pathway, the commercial study shows that it has a strong financial case with the capacity to introduce at existing and new refineries. MVR is likely to be one of the lowest cost method to provide if powered by the renewable energies, and also depending on the cost of renewable power as well. So it is likely to be the lowest cost method, which can be said that zero carbon process, or it can decarbonize partially or fully depending on the availability of the renewable energy sources. But despite several advantages and the benefits, there are disadvantages as well. There are certain challenges for implementation. The cost of retrofitting is heavily impacted by the complexity of the implementation and process tie-ins. Spatial requirement is also very huge. It becomes a very big challenge for retrofitting options. How can we set up in a compact area, confined area? The electricity requirement is high and is governed by the price of the renewable energy. Like here, I have set some KPIs like total refinery energy consumption, the steam consumption, power, CO2 emissions, and water consumption. So if we see that the steam consumption for the base case or the existing case goes down to like almost nil, the CO2 emissions are also lower, very much lower than that of the existing plants. Water consumption is also less because we are replacing the cooling towers. But similarly, the power consumption is increasing. So here, if we cannot supply the power with the renewable energy resources, then it will become a challenge. But overall, if we see that the total refinery energy consumption is reduced also, that is a big advantage as well. So with this, I have come to the end of my talk. These are some of the references that I have used for the presentation. And if you have any questions or queries, I'll be very much happy to answer. And lastly, thank you for giving me this opportunity to present at IBAAS 2024 Virtual Technical Lecture Series. Thank you.
Sir, please unmute yourself.
Thanks, Saprativ. Now the session is open for questions, answer, and discussion. Please ask questions to Saprativ.
Hi, Saprativ. This is Rosalie.
Yes.
So,
Hi, ma'am.
Yeah, very nice presentation. Actually, a burning topic right now. We are all looking forward for decarbonization of our refineries, be it the alumina, be it aluminium, wherever possible. So, my question was already you have also deliberated a number of times. Until and unless we are using the renewable source of energy, MBR is not getting supported. Like
not only renewable energy, we can use renewable energy, but the commercial availability and the cost economics has to be come down, because if we say that per unit of renewable energy is higher than the coal-fired electricity units, then there is no point of using this technology, right?
Yeah. So actually, we did a internal. We have also did internal calculation, and it was requiring some extra, as you rightly said, 3 times of the electrical energy consumption. So it doesn't make economic sense to, again, if we also want to retrofit our evaporation circuit at Lanchghat refinery, it's not. So I just wanted to ask, can you give some brief on what is the current scenario of the availability of the renewable sources in India or in and around, so that, I mean, the viability up to when we can look forward that we are getting this renewable source at a economic price. So any light on that?
Yes, yes. So basically, the thing is that now because of the availability of coal in India and because government is also pushing for solar, across the country, solar things are growing up. Then also the grids are newly set up by different companies. The solar, then there are wind technologies, wind turbines as well. But I would say that for the next 5 to 10 years, coal will be the most popular or economic source of energy as of now. But simultaneously, the setups are going. The companies are investing. That Vedanta is also, looking for renewable energy resources, importing energy from renewable sources. But to replace the fossil fuels completely, that will take time. Maybe 20, 30 years down the line, but not at near future. We cannot say that we'll completely replace the coal-fired energy. Yes, it will take time.
Yes, because you know, for MVR at evaporation circuit, it will be to power the MVR, you will need electricity, and also for
Exactly.
replacing the electricity which was getting generated by steam. For that also, it
Yes,
will be requiring additional
and,
electricity. It is
and
one
that
thing.
will be more even for the low pressure, low temperature alumina refinery. That
Yes,
requirement will be even more
even more.
because yeah.
For the replacement of steam,
Yes, yes,
so
yes.
that energy
Because
needs to be
because
also backed up.
currently it is serving two purpose. One is the electricity providing to the plant, as well as for the evaporation and other digestion processes. Yes. So
Yes, Nandi
yes.
sir, you are telling something.
Hello, sir.
Hello.
Yeah, this is Sanjay here. We have been
Hi.
associated with JS Group. Yeah. Saprativ Basu, sir. I have a question. Like as you said about the solar energy and other renewable energy, there is a drive towards H2O. Sort of a hydrolysis with that, making the hydrogen and using this. Can you put some light on that? That could be another sort of a way to get
Yes.
more
The
energy
I think
efficient.
I think you are saying about the electrolysis of water. Is it?
Yeah, absolutely correct. That's what.
Yes. Yes. Yeah. I mean, see, there are a lot of
And
opportunity.
utility of hydrogen into this,
Yes,
that's
definitely. I mean, more than the aluminum industry, I think steel industry is also looking for green hydrogen production. Because for the electrolysis process, and again, you need electricity to split the water. So that also requires some amount of fossil fuel or whatever energy used. But
no,
for
sorry for the interruption. I mean to say there is a combination of sort of,
yes,
as you have a solar, that
right.
energy you are using to, hydrolysis of this thing, and then you get this energy hydrogen for this.
Hmm. Definitely. I
That's
mean,
sort
for
of that is a hybrid sort of arrangement.
as of now, solar is one of the promising technologies that is available,
Mm,
and it is expanding significantly.
mm,
But as I said earlier, to replace completely the fossil fuel, that will take time. But it needs the policy changes as well, and also the availability, because a lot of areas are unorganized as of now in India.
mm.
So things will take time, but eventually we'll look forward towards that.
Sir, also one more point. There are a lot of drive by government regarding the CNG, that is biogas usage. From the
Yes.
biogas also, as you more than the automobile section, this biogas CNG usage into the industrial in steel and in aluminium. How do you think that stream in the future?
Yes, so for biogas, the thing is that it depends on the collection of the sources, right? So
Yeah.
if that sector becomes very much organized,
Yes.
then and also it depends on the quality of the sources. So what happens is in a part of the country, if the calorific value and all the
wet wet
measure.
wet wet sources and other things should be the which has got around
Yes. So
2200 calorific value. It has
yes,
to be more than 4
more
5000 above.
right to match up with the coal, the
Yeah,
industrial coal that we use.
yeah, that's yeah,
Yeah,
calorific
yeah.
value. No,
but
I'm looking into
but there are startups which are who are working on that. I
yes,
mean,
yes.
there are a lot of startups who are working on the biomass, and
Uh-huh.
eventually they also can be a promising energy source as well in near future.
Yeah, correct, correct. No, what I'm saying, my only question in a short was having this point of MVR, whatever you said is, if
Yes,
you have a sort of a another other energy sources, which energy can be generated through the other sources, like it has been more and more cycling. You know, that only the
right.
cost, net cost of the 1 ton of aluminum production with the scenario of the energy requirement after the whole churning of the process will come down to a realistic one. Am I correct or not?
Yes, absolutely, absolutely. Yes.
Actually, Mr. Saprativ, I am having a question. I am Nanta Gupta talking from NIMT.
Hello, ma'am.
I have gone through a presentation on aluminium refining, and the pollution which is being created during refining process creates lots of pollution, and that's a problem the West is facing today. So, what about your views regarding it?
So for the West countries, as I said earlier, that the availability of natural resources apart from the fossil fuels like hydro, then there are LNG or the natural gas. Those are much more higher than that we get from the in our country. So depending on the sources of the energy, it will eventually build up. Right now the sources of natural resources from which we can generate the energy is not that much in India. So
Okay.
that will take time, because right now if we want to even apart from solar, wind, if we want to generate electricity from renewable sources, we have to import. And also that becomes a costly affair.
They are making a comparison of like the aluminium is the best metal, a substitute of steel and iron nowadays, and because of this problem, it is very difficult to cope up the benefits which is due to the
Right,
aluminium and aluminium alloys. Thank
right,
you. It's
right.
a nice presentation. Thanks a lot.
Thank you, ma'am.
Very good, Saprativ. It was a really good presentation. And I will request if there are some more questions to him, or the presentation is available on IBAAS website, and his coordinates are available. You can contact IBAAS office, and we can forward all the questions to Saprativ. But anyway, if you have any question, please ask Saprativ. So how do you think it will industrialization is okay? There is a question.
I think Swapnil has some questions.
Swapnil. Yeah, Swapnil, please.
Very informative lecture on MUR. I think you mentioned about some trials conducted in Australia on MUR. Okay, so we just wanted to know, have they made any cost comparison? Have they published these results?
Yes.
How it was in terms of cost, in terms of pollution or CO2 emissions?
Yeah, so they have done a feasibility study, I would say. I mean, for the trial, they have not actually, published the results. But for the feasibility study, what they are saying that, as I showed you earlier in the presentation, that the cost of, steam production is completely eliminated. So, are very much nil, minimized, I would say. So, in that terms, it has around huge cost benefit for the MVR technologies that they are predicting. But for the almost, I would say that reduction by around 25-30% in the cost, I would say. But for the actual trial, I couldn't find the report. They have not published yet in the public domain.
Okay. Thank you.
Hello.
Hi, Dr. Lipak. Hello.
Yeah, this is Dr. Leepak from NITK. So actually, this presentation was nice on MBI technology.
Thank you.
So you mentioned that it reduces the CO2 emission and overall energy consumption is less, but the power consumption was high.
Yes, yes.
So
So
can't
that's
it be
why.
met by?
Yes,
Yeah.
that's why we
Can't
need
it be met
to.
by like? Yes, yes. Continue.
Yeah, so power consumption is high. That is why what I said earlier, that power requirement for the compressor or the MVRs need to be sourced from the renewable energy resources. Then only we will have lower carbon emission. Otherwise, if we are taking it from the fossil fuel or the steam generation plant, then the cost of production will be higher. So then there is no point in using MVR. It
So if
only
this
has to.
MBR
Yeah.
if this MBR is installed in suppose already established alumina refinery, how is the capex is there? Is it very high or is it comparable? Capital expenditure.
Yeah, so capital expenditure is high on the higher side because of the this compressors cost is huge, and also we have to for the retrofit option we have to the pipings and all those things need to be done properly. So but eventually the steam if we see that in the cost of production, it eventually comes down because we are eliminating the maintenance is completely very much eliminated, the maintenance cost, the operational expenditure. So though the capital expenditure is higher, but due to very low maintenance cost on the operational cost, eventually the cost of production comes down. Yeah.
So
That
yeah. So last question is yeah. Thank you. The last question is this technology tested on pilot scale or on
not
full
no
industrial scale?
so for the I can say for this study that Alcoa has been doing, they started in 2021, and after completion of the study they were supposed to do the trial on 23 or 24, but right now they have postponed it by 2 or 3 years. I don't think they have taken the trial. But one, not in alumina industry, but one chemical industry in Turkey, they did for a very low scale evaporator. No, they have done this type of trial, and they have back in the year 2016. I think then they have seen some benefits after using it, but again I don't think they have scaled it to the industrial scale. So that is there for alumina
Thank
refining.
you.
I have not seen any commercial implementation. Yeah.
Thank you very much.
Sir, Saprativ sir.
Yes, sir.
Yeah, thank you. It was a very nice presentation, and nicely, I want to just ask you one thing. Since it is a pilot project, as you have mentioned, so the payback period and other thing on what, suppose something started with a little cost of the project, but with a faster, payback period, those calculations are to be established. And
Yes, absolutely.
then then only this they could find out one ton of aluminum and what. Correct or
Right.
not?
Yes, absolutely, because these are all feasibility studies, and I mean, show a potential for towards decarbonization, but all those things, cost optimization, all those things needs to be done. Yeah.
Thank you, sir. Thank you for wonderful presentation.
Thanks.
Thanks, Saprativ, for good presentation. And we will look forward to meet you in IBAAS conference in Goa.
Thank you, sir.
Okay.
Thank you very much.
Thanks.
Thank you, Saprativ.
Thank you, ma'am.
Okay, so that's over, and we will look forward for next series lecture. Bye.